Hey guys, welcome back to another coding interview question. If you're new here, my name is Michael. I'm a computer science student and I solve coding interview questions. So today's question is the branch sum question. So what this question wants you to do is to sum up all the values in a particular binary tree branch and add that sum to a list and return a list of all the branch sums. So what do we mean by that? So let's say, for example, you have a binary tree of 2, 3, 4, 1. Let's say, what could this be? This could be 3. Let's say you have this binary tree, right? And this question wants you to add up all the values in this branch, that's this branch, and that sum would be 2 plus 3, 5, 6, so that would be 6. And take another branch, that is this branch, right here, and that sum would be 5. And take another branch, that would be this branch, that sum would be 8. Take another branch, that would be this branch right here, and that sum would be 7. So this is it. You go through 2 plus 3 plus 1, and the sum is 6. You go to 2 plus 3, that's 5. 2 plus 4 plus 2, that's 8. 2 plus 4 plus 1, that's 7, and you return a list of 6, 5, 8, and 7. So what do we do in this case? Well, first of all, we have to traverse the tree in a depth-first search way. That means we have to go depth first, and we need to know when we've hit a leaf node. And the leaf node is the very last node in the binary tree, that's the deepest node, that doesn't have like other children nodes to it. So say, for example, 1 doesn't have other children nodes, 3 doesn't have other children nodes, 2 doesn't have other children nodes, and this 1 doesn't have other children nodes. So all of these are leaves. So what we do is we traverse the tree in a depth-first search way, and we keep adding the sum in the depth-first search traversal. That's like a pre-order traversal. And when we hit a leaf node, we add that sum to a list. So we're going to do that recursively. There's also an iterative solution to this. I think I might cover it if we have time. Let's see what happens. So I'm going to define a function, and that would be a list. It's going to take in integers. That's what we want to return. And let's call this branch sums. And we're going to have a binary tree. Let's call the root node, and this would be all that we would be given in a real life situation. And we have to return the branch sums, right? So I'm going to create another helper function, and this is going to be an overloaded function because they're going to have the same name but take in different parameters and arguments. So it's definitely going to take a binary tree, and this would also be root. And we have an integer for the sum that we're going to be incrementing. And we have another, what else do we need? We need a list that we're going to return, and that would be list integer. Let's call it to return, or sums. All right, or sums list. All right, okay, this is gonna be, let's make this lowercase. All right, so first of all, if the binary tree is empty, then we just return nothing. So if root is equal to null, and there's nothing in the binary tree, there are no branches to sum up, then we just return sums list, right? Sums list. Otherwise, if there are other things to traverse, if there's a value in that root, all we want to do is to add that to the current sum. So sum is equal to, let's say, plus equal to, and what are we going to add to the sum, to the current sum, that's the root.value. And if this is a real like interview situation, you're going to have another class that initializes a binary tree called root, and it's going to have 3 attributes, and that's going to be left, right, and value. Okay, so this is arbitrary for now because we don't have a property of root that's value, but we know that's exactly what's going to happen in an interview situation. So this is the same as sum is equal to sum plus root.value. All right, so then we add the current root.value. All right, then we want to check if we're at a leaf node. And if you could remember from our example, a leaf node is a node that doesn't have children nodes. So if root.left is equal to null and root.right is equal to null, then with here to lift node, LEF node. So when we're at a lift node, we know that we're at the final node in the branch, so we want to add the sum to the sums list. So we want to say sums list that add, what are we adding? We're adding the sum, okay? Otherwise, if we're not at a lift node, then we want to keep traversing through the other nodes. And so if we have a left value, if we have a left child, root.left is not equal to null, then we pass in that left child to the recursive call, okay? And that's going to be branch sums. So this guy right here, the same root.left now, same sum, and sums list. We're going to do the same thing for the right child. If root.right is not equal to null, then we pass in branch sums of, we pass in the right child node, sum, and sums list. Okay, terminate this. When everything's done, we want to return sums list, because we know that at the end of everything, we've added all the branch sums to the sums list. Then we just want to return it. And we just have one more thing to do now, and that's to call this function in this, the main function. It's not actually the main function. We want to call the helper function in this other function. And we simply just say return branch sums, that's this guy right here, and pass in some parameters to it. It's going to take root, that's for the binary tree, because this root is going to pass into this root. Then the initial sum is 0. So why is the initial sum 0? Because at the start of everything, we don't actually have a sum yet, and we're hoping to increment the sum at this point. We don't want to have an initial value other than 0, okay? Then we want to pass in an array list for the sums list. So let's create an array list. So let's call it sums list. It's going to be the list of integers. Sums list is equal to new array list. Close this guy, and we pass in sums list. And we're done. So that's it for the recursive solution. Let's quickly dive into the space and time complexity of this algorithm. For time complexity, let's look at what we're doing. So we're going through every node in the binary tree, or every node in every branch, and adding that node's value to a sum. So that would be O of n, because we're going through every node. Now for space complexity, this is going to be a little bit trickier. So let's look at what we're doing, right? we're going through every node, we have a sum, and we're adding that sum to a list, right? So you could naively say, well, space complexity is O of S, where S is the number of sums that we're storing in the sums list. You would be technically right, but we're also doing recursive calls in the algorithm, and the way recursion works is that it adds calls to the call stack, and that accounts for extra space. And that space is more than the number of sums that we have, because every call we make to the call stack signifies a node in the binary tree. And there are more nodes in the binary tree than there would ever be sums. So if you really want to be technical, the space complexity is going to be O of S plus n, where S is the number of sums and n is the number of nodes. But in big O notation, we tend to take into account the largest value, because when this grows, this is going to be very negligible, okay? So the actual space complexity is going to be O of n. That's it. So time is O of n, and space is also O of n. So that's it for this video, guys. I'm also going to do the iterative solution in another video, so watch out for that. If you like this type of content, please consider subscribing to the channel and support your boy. Like this video for the YouTube algorithm, and also post your comments down about this algorithm in the comment section. Share this video to your friends and family who might be preparing for their coding interviews or have an interest in code. And I'll see you in the next solution. That's the iterative solution. Bye.